Thanks very much.
Okay, thanks. Well, good evening, everyone. I'm Ernest Artiaga. I'm the CTO of Albora. Albora is a small startup. We have people distributed between London and Barcelona. And we define ourselves as a company that does next generation satellite-based geolocation with high accuracy, sensitivity, and security. And the next generation is because we believe that things are evolving and the current generation, the traditional approaches are not enough for the new, the things that are coming. So we try to focus on the issues, and what I would like to share today is which are the issues that we have identified that could be an issue, a problem in the next times, and also, of course, which is the path that we are taking to address these issues. So we will not go so down into technology, but which are the problems and which are the possibilities to solve them. So basically, these people that we have here, they were the inventors of the GPS technology. As you can see, they are not young. The GPS technology was invented in the 70s, in the early 70s, and it is still working. So it was robust, it's working well, but it's starting to show some limitations. Basically, the algorithms that we are using now in our current receivers, the ones that you use in your mobile phone or the ones you use in a tracker for your car or a truck, basically use evolutions of these original algorithms. Of course, in better hardware, of course, with some optimizations, but they are still basically the same. So in a way, we are navigating in the modern world with some technology that is a bit old. So what is the consequence of this? This is a screenshot from an iPhone taken in London. So this iPhone is using all the wonderful new technology with small chipsets and all we have, but still you can see on the top left the actual position when this screenshot was taken, and the position according to the iPhone. So it's quite far. So even using in a city that we are supposed to have Wi-Fi's, that we know where we are, all of this, the position is quite far from accurate. And we wanted to examine this, if this was common or not. So basically, we sent some of our engineers that, in the London office to take measurements, because this is the basis of engineering. We went to a special area of London. This is the area of Canary Wharf, which is basically a place surrounded with high skyscrapers, with a lot of crystals, window, metal, and we have a park in the middle. So this is what you see in the bottom. So you see a small green star with this real position of our antenna, the receiver. And we took some commercial receivers, GPS receivers, medium grade, not the most expensive, not the less expensive. And the red lines were the positions that these receivers were giving us over the time. So again, we can observe that in these complex situations where you have tall buildings that cover the signal from the satellites, and you have a lot of reflection or multipath, it is called multipath situations, GPS or GNSS in general is not working as we would like. If you let me introduce a bit of teaser here, I can say that, for example, the new generation algorithms that we are using actually get a position about 3-4 meters from the actual one. So it's just to know that there is room to improve and we can do things better. This is something that happens not only in urban areas, but it's also an issue in industrial areas. So if you have to a manufacturing plant, if you go to a chemical plant, for example, you will have lots of tubes, lots of pipes, which are basically metal, and they produce similar effects to high buildings. They reflect the signal, and they cause interferences, and they produce bad results in location. And now we have another issue, which is basically security. So this is something that was reported about November last year, happened in the Shanghai port. And basically what happened is that there was an attack, a spoofing attack. So someone faked the signals from the satellites and suddenly all the ships that were in the port disappeared from the port, according to instruments, and appeared inland. So on the top left diagram, you see this circle. So all the ships left the port and started running in circles in the mainland. Of course, you can imagine that this caused a lot of trouble. So is this a problem? Who can afford this kind of thing? So the situations that we are here is something similar to what happened with IT security a few years ago. At the beginning, when there was the origins of internet, no one cared about security because very few people were using that. Only the military cared about that. But then it went popular, and now no one is browsing or navigating through internet without having HTTPS and without being careful with all the security aspects. We believe that this will happen also with GPS. Now GPS is used in big infrastructures, also in our mobile phone. But if we evolve and we start using self-driving cars, drones, and all this kind of stuff, it will be very dangerous if we don't take care of these kind of things. The problem with security attacks is that the attackers normally have a lot of imagination. So you can prepare some kind of defense for this attack, the particular one that caused this issue, but you can be sure that in a few months, you will have a different type of attack that will use a different technique that will overwhelm the safety mechanism that you designed for this kind of situation. And of course, if we are talking about self-driving cars, this is actually an issue. We don't want them to go crazy on our streets. So which is the problem that we have identified? Most of the traditional approaches are based on hardware. So most of the GPS vendors are hardware vendors. They send you a piece of equipment with the latest technology, but hardware is normally expensive. So getting high accuracy and security means that you have to get a very high-end piece of hardware. These devices become obsolete because of the same reason that we just mentioned. So if we are trying to defend from attacks, the attackers will evolve and your hardware will become obsolete. Again, I come from a computer science background, so I can remember 20 years ago, the security in IT was based on physical firewalls. So this was a massive piece of machine that you connected your data center on one side, the internet was on the other side, and this machine was supposed to protect you. What was happening is that a few months later, you were changing from 100 megabytes to a 1 gigabyte bandwidth network, and this machine was obsolete, so you had to change it. Then you had 10 gigabit, you had to upgrade again, and this was every time difficult to upgrade, expensive, and complex. So what we are trying to do in Albora is that we are trying to follow a different path. So we are leaving the path of hardware, and we are trying to do geolocation based on software. And we are following the hints that, for example, the CEO of Amazon Web Services is doing. So when he was talking about IoT, he was saying, okay, what we have in IoT, we have very small pieces of hardware with very limited capacity, but we can connect them all to the cloud. And what we do is that we provide the intelligence from the cloud. So we believe that this can be done also for geolocation. So we can simplify the hardware that we are using to receive the signals, and we can upload the information, the raw information, and do the processing on the cloud. What you may argue here is that, okay, yes, but the cloud is always far, it's slow, you take some time, there will be latency problems, you need a bit of velocity for this to be practical. And this is where we believe that the next piece of technology will help us. Currently, we are talking about deploying 5G networks. Big companies like Intel and IBM, they are investing a lot on edge computing technology. So this means setting up computing elements near the place the computations are used. And this offers us a big opportunity to actually reduce the latency, distribute the computations, and make this computation near the asset that needs this geolocation, reducing the problems with latency. So basically, what we are doing is evolve this model based on hardware in a model that is based on the cloud or based on the edge. And we don't sell pieces of hardware. We believe that the future is selling services offered from this edge or this cloud equipment. So this is basically the model that we are developing. We have our asset, which may be a vehicle, it may be a critical infrastructure, it may be different things. We still receive the satellite signal from the satellites. What you actually need for this is a very simple radio receiver. This is the basics, and you can buy this off the shelf from any place. You need some small capacity to pack this signal and send it to the cloud. And just to let you know that how simple this may be for our test, we are using a Raspberry Pi. So we are connecting a radio receiver, a Raspberry Pi, all of them bought out of Amazon, basically. And you can build your hardware. And then we send the data via 5G or via other communication mechanisms to the edge. And there we can apply algorithms and compute, process the signal, apply new generation algorithms, and get more accurate positioning for our assets. The other interesting thing here is that as things go evolving, we have more constellations on the sky that we can use. We have new advances in signal processing. We have more things that we can apply. Applying this on the cloud based on software is very easy. So this also opens us the path to do lots of improvements with relatively low cost, because the basic hardware is still the same. Even if your algorithm is very advanced, what you need in your asset is something that receives the signal, a radio receiver, and a transmitter to send this to the cloud. The other thing that we are trying to take advance is the infrastructure that is being deployed in cities and other infrastructure. So many cities are talking about deploying 5G antennas everywhere. We have smart cars that even if they are not self-driving, they have equipment that they can communicate with the city infrastructure, and they can communicate even with other cars that are in the surroundings. So we may even use things like having some part of the computation in some special vehicles. For example, we can use the public transportation of a city to install some computing element on buses, for example, and take this and communicate the information to the surrounding vehicles. And we can basically move on and take advantage of all this smart city infrastructure that is being deployed in cities. So basically, which are the benefits that we are taking with this kind of approaches that we think that help solve these issues that we identified with geolocation? Basically, we have redundancy, because of course, if you want to have a low-end receiver on your asset or on your car, you can still have that, but you have the support of an external tool that comes from the cloud and can act as a verifier that the information from your local receiver is actually good. And this is very useful, for example, to detect jamming and spoofing attacks. So we can apply complex algorithms to detect attacks in the cloud that are not affordable for a hardware piece. And at least we can alert the vehicle that say, okay, be careful, this signal that you're using to try to identify your position, maybe it's wrong, because our intelligence system says that probably you are under an attack. So maybe you should rely on other sources and not just the GPS signal, for example. We can apply here the economies of scale, so we can have affordable prices, because we update the algorithms once in the cloud or in the edge, and we can apply all these advantages to all the receivers with relatively, well, not relatively, but much lower cost than if you have to replace all your hardware equipment in all your assets. We can provide different services like integrity or quality of services. And as I mentioned before, we can do very easy upgrades. So the bottom line is that by changing this approach from a hardware-based technology, which is what we have mostly nowadays, to a software-based technology, we have improved in functionality, we make the maintenance easy, and we can also facilitate the integration with other services, because we can provide APIs and we can provide support for example, open hardware and other equipment. And well, this is basically it. So thank you for your attention. And if you have any questions, I would be glad to answer. Thanks.
Thanks very much, Ernest. I'm sure we have some questions. Let's quickly applaud everyone. All right. Good talk.
So, Ernest, I've got a question here for you. Sorry, I got muted there. Can you hear me now?
Yes, we can hear you.
Cities, at least in Europe, and especially since the virus, are rapidly changing to encourage different types of transport, more walking, cycling, scooters. Is there a risk that autonomous driving software and applications are being designed for cities as they were, not as they are becoming? You're muted.
Sorry.
Good. Can you hear me now? Yeah.
Yes.
Okay. So yes, the paradigm may change, but I don't think that this will be a problem for autonomous vehicles, because actually in times of COVID, for example, here in Barcelona, what we are observing is that actually there is an increase in private transportation, because of basically people is scared of using the public transportation. So there's an increase. The problem that we are having now is that as everyone is taking the car, there are more traffic collapses and so on. Actually, we were in discussions for a project in Albora about, in some city, I cannot disclose, but they were worried because some types of public transportation in large cities were actually causing part of the problem, because they were mixing with private transportation and they were causing accidents, traffic jams, and all this kind of stuff. So actually cities were very interested in automatic public transportation, both in terms of buses, but also in smaller units, to support this kind of, okay, telling the people you don't have to take your own car, you can have some kind of automated car sharing, and this could be a good way to go in the future. Of course, this is not yet here, but this is supporting these kind of things. In terms of using other transportations, like for example, e-scooters and all these kind of things, they also have an issue. They have a different issue. So the issue, of course, is not autonomous driving, because you have a human on top of them who is driving the e-scooter. But the companies managing these fleets have a problem, because it's very easy to miss one of these e-scooters, for example. Imagine that you are leaving your e-scooter in this park in Canary Wharf, the one in the photo. If you have your application in your mobile and you're telling the next user, okay, go there and pick your e-scooter, you will be sending them about half kilometer away. And of course, if you have your user looking around, this is a problem. So even in this case, the use case is completely different from a self-driving car, but you still need good location in a urban area, because you want to find where your scooter is, even if it's a human driving it. So I think that use cases are different, but the technology is useful for both of them.
I get you. One last question for you from Chris. He says, you mentioned edge computing. How much benefit does that give latency-wise, and is it vital for your use cases to work?
Good question. So basically, the problem with cloud computing is that in terms of latency is very unreliable. So for example, we have one of our teams here in Barcelona, but we are using the Amazon side, which is in Ireland. Which means that there is a long path if we are trying to get measurements here up to Ireland, going back. And of course, this depends on quality of service, and this depends on a lot of issues. If you are using, for example, 5G, and you have an antenna of 5G, and you have all the routing equipment to translate these 5G communications into internet communications, you need a computing equipment. And the problem for the manufacturers of computing equipment, but the advantage for us is that nowadays it's very expensive to build low-end computing equipment. So it's much easier to have your 5G antenna with a fully fledged processor and a lot of computing capacity. So that means that basically you have a direct line of sight between your vehicle, for example, and the 5G antenna, which is relatively near. You have some computing equipment which is relatively powerful near your antenna. And the speed of this is very fast compared with the speed that you need if you will have to go convert this to a central place in a cloud and so on. And the other advantage that you have is that as you only have to process the vehicles or the assets that are surrounding this antenna area, you're also processing much less information. So you can still rely on the cloud for analytics, for fleet management, for all these kind of things. But if in terms of responsiveness, using edge and using technologies like 5G can be a big advantage. Of course, this still has to be deployed, so we'll see. But it's what we see that we believe that will be the future.
Thanks a lot, Ernest.
Yes.
Thanks to you.
Thanks very much, Ernest. Okay, so